Hi everyone. In this video, we're going to start chapter 4, section 2, which is going to talk about the CDF of a continuous random variable, and so how do we get a CDF? And it's going to talk about the moments of the distribution, like an expected value or variance. So we're going to see how those translate from discrete distributions to continuous ones. So for a continuous random variable x, the CDF function of x, which we denote capital F, is defined in such a way as this below. Now, this is just like the discrete distribution, the CDF of a discrete random variable. The only thing that's different is that the sum is now an integral. So before, for the discrete situation, it would have said equals the sum over. For a discrete situation, it would have said the sum over all x up to let's say up to a certain point x. I forget how I defined it previously, but it was said up to a certain point x of f of x dx. And so we've got basically the same thing here, but we change that sum up, sum to an integral, which is what I've been sort of repeating is the difference between these two. And so we've got an integral from everything up until x, so from negative infinity to x. And then, of course, if I have x in my integral bounds, I can't have x in the actual function. So we've got the PDF of the random variable x, f, but I just replace x with a dummy variable y. Okay, and so it doesn't really matter what's inside the parentheses as long as it and then the d, whatever it is, stays the same. Right, so in words, what the CDF means is that as we know before, it's the probability that a random variable takes on a value of at least x, which means in this case, when we're now dealing with probabilities or PDFs that look like curves instead of just like probability masses at a point, we're again finding the area under the curve. And now, instead of just between two numbers, which was sort of how we used to define a PDF in general, it's going to be everything up and until a number. Okay, so that's sort of what we're showing over on the left graph at the bottom, is that the CDF evaluated at 8 for some example where the PDF goes between 5 and 10. There's the area under the curve from the beginning of it, which looks like 5, up until 8. All right. Similarly, there's a sort of graph of the CDF. And before, I don't know if I really mentioned one for the discrete distribution, and I failed to mention it, or didn't mention it, because it looks kind of odd and would probably have tripped you up. But here we've got sort of a simpler thing, is that the CDF function is just going to be another curve, a different curve here. And the height of the, of course, line represents the CDF value at that point. It has to level off at 1 because I can't have probability more than 1. Okay, so we aren't going to worry too much about the actual graph of the CDF, but it's important to know what it looks like. It's going to be always decreasing, so it always will go up, or at least stay constant, and then it'll eventually level out at 1. No matter what happens, no matter how slow it goes up, it's always going to start at 0 down here and end at 1. But that's the CDF of a continuous function. So let's find the CDF. In other words, let's use that integral that we see there. And so I guess actually before we do that, we should look at some rules. Right? And so this is interesting because we can compare, sort of contrast with what we saw before with a discrete random variable. If I want to find the probability that x is greater than, or really, we could also change this to greater than or equal to, it's going to be 1 minus f of a. This is in contrast to the discrete situation, where the answer would have been one minus f of a minus 1. Right? Because that equals 2 made a difference there. Now it doesn't. Okay, and then down below, this is like what you wanted to believe for a discrete distribution, a discrete random variable, that to find the probability that x is between 2 points a and b, it's just f of b minus f of a. And they show you a nice graph down here. Okay, how do I get the area under the curve from a to b? Well, I'd start with b, and that gets me everything I want, but it also gets me a little bit more than I want. And so how do I get rid of that? I subtract away a. Again, in contrast, for the discrete situation, depending on what happened, the rule was f of b, it could have been f of b minus 1 minus f of a, or f of b minus f of a minus 1, depending on inclusive or exclusiveness. Okay, but now that's not true. We get the easy just f of b minus f of a. So everything works out more nicely in a continuous world than in a discrete world. And so let's get practice calculating the CDF of a uniform distribution. So again, we defined a uniform distribution earlier on in our slides, and I'll do it again here. If we let x have a uniform distribution, I'll call it u, and a uniform distribution is defined by its lower and upper bounds, so I'm going to call that lower bound a and b. Okay, means that the PDF of that function is defined as 1 over b minus a when x is between a and b, and 0 elsewhere. Okay, and so to find the CDF function at for x, that's the integral from negative infinity to x of the PDF, or rather I should say f of y dy. So unlike the discrete situation, we're actually going to have another formula. So this up here signifies or designates the curve. So this is the shape of the curve. That is the density. Okay, and then we're going to get a whole nother formula which represents the curve for the CDF. So before we just had to add up PMF values to get to the CDF value, but now we actually have a function that we can just substitute a number in, and then out we're going to get the CDF value at that point. So we have our function f, okay, and then we have our bounds, negative infinity to x. And so let's let's simplify and substitute. Now, because x is defined only on the interval a to b, really the integral that I'm taking here is from a to x. It's from that lower bound up to the upper bound. Because anywhere between negative infinity and 0 and a, whatever a is, that that PMF value, the density, is 0 there. And so I don't really care about negative infinity to a, I only care about from a to b. That's the only where it's defined. And so I have the integral from a to x of 1 over b minus a dy. So I take the antiderivative. I get y over b minus a evaluated from x, or from a to x. And then I get x over b minus a over b minus a. So when I combine those, the CDF, capital F of x, equals, at least in part, x minus a over b minus a. And that's defined when a's between, or when x is between a and b. Okay, so then the full CDF actually has to include 3 different parts. And the first part is what happens before a. You know, what's the CDF value before a? Sorry, I'll make it better. What happens when x is less than a? Well, the CDF value there is 0 because there's sort of no positive probability until a happens, by definition of the PDF up above. So before a, it's 0. During the interval a to b, the CDF is x minus a over b minus a. And then after that, after we get through all that, when x is greater than b, the CDF value is 1, because it sort of all happens between a and b. Once I hit b, I have hit like sort of the full probability I can use because it's all between a and b. And so then it's 1 afterwards. By definition of a CDF, it's always going to end at 1. Okay, and so this is the full CDF for a uniform distribution. Okay, so I'll leave that and pause here just for a second so you can finish writing this down, looking over it. Feel free to pause the video at this point and look at all the work that I've done and see if you have any questions. So here's your turn. Okay, I give you an example. Suppose the PDF of the magnitude x of a dynamic load on a bridge in newtons is given by the following formula: 1/8 plus 3/8 x when x is between 0 and 2. Okay, I want you to find 3 things. So I want you to find the CDF. Okay, then I want you to find the probability that x is between 1 and 1.5. Again, using the rules that I talked about, the rules of the CDF that I talked about, and also greater than 1. So each of them match the 2 rules that I talked about previously to doing the CDF of the uniform. Okay, so do that for this first video, and that's the end of this first video.